thank you for coming out to the session on elegant async patterns and functional programming techniques that you guys can use right now to scale to multi-core JavaScript. What does that even mean? We'll get to that. So just a little bit about me. I'm Jonathan Martin, or at Nibbler on the web. I'm an instructor and web developer for these folks. We're a 16-week coding boot camp just up the street. We're called Digital Crafts. I won't do too much of a sell because this is Creative Circuits. But if you do come across the motley crew of folks back there eating all the tacos, those are my students. And despite listening to me for 6 hours today, they're here to listen to me again.
Extra credit.
Yeah, extra credit. And then they're going to restart that cycle and come listen to me for another 6 hours tomorrow. It's really stupid.
Yep.
Now, outside digital crafts, I have a little bit of a different life. I'm a digital nomad, which means that I leverage technology to work pretty much from anywhere in the world. Over the past 3 years, this has kind of been how I've nurtured a lifestyle of landscape photography. So if you don't like JavaScript or multi-threading, which I might ask, why are you here? Why are you at a JavaScript meetup? Well, anyway, if you don't like any of those, you can go look at pretty pictures instead, or learn what it's like to become a digital nomad. So I've got this up, yellowscale.com. For now, I'm going to assume that it is not the case that you don't like JavaScript, because hopefully otherwise you wouldn't have shown up. So a little bit of background about this talk. I recently gave this talk at a conference in Budapest, and I was really excited at the time, so I started to piece together some travel plans. And so I'm slightly obsessed with to-do lists. So I just started out listing things that I need to complete before I went and spoke at this conference. So obviously, I need to fly to Budapest. Kind of a key prerequisite. But also, there were a lot of other things I needed to do to get prepped for this engagement. So I needed to work on some slides as well. I needed to do a little bit of packing. There was a phone call or two I needed to make in terms of accommodations. While I was on the flight, I figured, okay, what am I going to do on the flight? Maybe I'll read a book, and then sometime before I give my talk, I should probably take a shower. Minor details, they tend to be kind of important. So lists are great and everything. But to start knocking out all these to-dos, I needed to figure out a plan for completing them. So I could just go from top to bottom and complete these to-dos kind of one by one. But in that case, I probably would never have flown out there since the slide deck wasn't actually complete until hours before I went and gave the talk. If I were to be more honest, I would have said minutes before. But that's one strategy I could have used to get all this stuff done, is I could just go one by one and finish one at a time. But I'm human, so of course I would never actually have completed these one by one. I might actually have worked on this slide deck on the flight and taken a phone call at the airport, but I definitely have to pack before I leave. So what I'm getting at is that we're always doing more than one thing at a time. And sometimes those things have to happen before others, and some can't happen at the same time. So if I were smarter when I was writing my to-do list, I would encode constraints and preferences for how I plan to tackle that to-do list. So for example, I could encode my constraints, these has to happen before relationships, as arrows. And these show that some things logically have to happen before others. For example, I have to pack before my flight, and I have to fly before I can speak at the conference. Moreover, I have to work on my slides, but that can happen really any time before I give the talk, so long as it happens before I get up on stage. And I can work on them, say, before or after the flight. It really doesn't matter when I do it. So some of these things can't happen at the same time, on the other hand. For example, I can't make a phone call while I'm on the plane, or I probably wouldn't read a book while I'm in the shower. Just wet books, not a great idea. So altogether, these describe my constraints and my preferences for how I will get ready for giving my conference talk. Software also deals with to-do lists of its own, and the problem is really twofold. We need a way to model our constraints and preferences foremost, and we also need a way to figure out a solution that satisfies all those constraints and preferences. The way we solve those problems is a defining characteristic of a lot of different programming languages you guys may already be familiar with, including JavaScript. Now, before we hop into the body of the session, I want to recap a little bit of terminology, because I'm thinking about my cohort back here, and they're like, Jonathan, what are you going to talk about? We haven't talked about multi-threading or the event loop or all that. So, for their sake, and for the rest of you, because I know that many of us are like, wait, event loop, this is a thing? So we're gonna recap that together. So in particular, I'm gonna be tossing around two terms quite a bit, and that is concurrency and parallelism. Try saying that 2 times fast. Concurrency, parallelism.
Concurrency, parallelism.
Thank you. Now, concurrency really just means that two or more computations have overlapping timelines when they're being executed. So for example, task 3 here begins before task 2 and task 1, but before task 3 completes, task 1 and task 2 will begin executing. Now, how you achieve concurrency is really up to you or up to the programming language. For example, one strategy you could use is you could very quickly switch between working on these 3 tasks to give the appearance that things are happening simultaneously. In particular, we use a technique called multi-threading to do this. Most modern machines, all modern machines hopefully, support multi-threading. And all it means is we have these 3 tasks that could run on a single CPU core, which can really only do one thing at a time. But with context switching, it seemingly does all these tasks at the same time because it's just very rapidly going and hopping back and forth between these 3 tasks. But there's another way we could do this. We could have 3 separate machines altogether, 3 separate computers or 3 separate CPU cores, and dedicate 1 core per task. This specific form of concurrency is an example of parallelism. So just to summarize, concurrent programs can run multiple pieces of code independently, and multi-threading and parallelism are just 2 execution strategies for running code concurrently. Now, how we actually end up writing our code won't vary too much based on the style of execution we go with. It's just that for the duration of this talk, I'm not going to really distinguish between the 2 of them, so I'll just refer to them collectively as concurrency. So in a nutshell, concurrency, doing more than one thing at once. Doesn't matter how you do it, it just happens. Now, I saw a few folks with a furrowed brow, and they were like, wait a minute, multi-threading, multi-core. This is a JavaScript meetup. Come on, we don't talk about these things. So Node and front-end developers alike are really commonly trolled by that classic question, how do you create a JavaScript code base since it's single-threaded? A lovely loaded question for you. But in fact, not only is JavaScript multi-threaded, JavaScript is highly concurrent by default thanks to a mechanism we call the event loop. But at the same time, it shields us from a lot of the multi-threading woes and synchronization primitives we might be used to in other languages like C++ or Java. So for example, here are 3 async APIs we might use in JavaScript. Every single one of these seamlessly fires up a separate thread in the background for a total of 4 threads, the main orchestrator thread, plus 3 others in the background, which basically means JavaScript is doing 4 things at once without us writing any special code. At the same time, that makes the AJAX request with the fetch API, right after it starts that, it begins scheduling a refresh function to be called in 5 seconds. Right after that, before it's even waited 5 seconds, it starts doing a database query. All of this happens asynchronously. It's something we take for granted in the JavaScript world. What's much harder, really, is getting our minds wrapped around how does it handle this and how can we take advantage of it instead of being frustrated every time we're like, oh man, I wish I could just block the event loop, whatever that means. So for that, we're going to take a step back. If JavaScript is multi-threaded, how is it that everything seems to be running on one thread, which means there's only one thing happening at a time? There's only one function executing at a time. How does JavaScript manage to keep this beautiful facade for us and at the same time do multiple things at the same time? That's where the event loop comes in. Now, I can't do full justice in explaining the event loop, so I'm just going to give you guys a really quick recap. These guys are going to get the in-depth recap. And just keep in mind, I'm giving you a really grossly inaccurate version. I'll send you guys to a much better explanation of the event loop later on. So here's kind of a layout I'm going to use for the next few slides. In the middle of this slide, we have what we call the call stack. Again, grossly inaccurate here. I'm just going to pretend that the call stack is how we keep track of what code, what line of code is currently being executed. A lot of you, especially those of you who actually have a degree in this, are like nodding your heads and saying, yeah, we know better. That's okay. On the far right, we have the built-in web APIs, or Node APIs if you prefer. These are natively implemented APIs that you can use right now, like DOM, or AJAX requests, or IndexedDB, or timers. And then finally, on the far left, we have our source code that we're executing. So first, we're performing an AJAX request and executing a function called parse, a callback, once we receive an AJAX response. Then next, we use the setTimeout API to schedule a refresh function to run in about 5 seconds or so. And then last, we use the IndexedDB API to make a database query and invoke another callback called render once that query has completed. So those are the different lines of code you see. So how's the JavaScript runtime going to manage to execute all 3 of these seemingly simultaneously? Now, some of these operations will take a while. Some are much longer than others. That AJAX request could take several seconds. It might never finish. So let's evaluate that code ourselves and build up our understanding of the event loop. So as soon as the fetch function is invoked, a web API is fired up, which is implemented natively. We're going to show that on the left by sending that little parse callback from the call stack and sending it on over to the web APIs. These are things that are natively implemented that the browser has provided for us. But we don't just fire up that fetch API, we tell it what function or what callback to invoke once fetch receives its AJAX response. So this is sort of how we ask the browser, once you finish doing your thing, which you know how to do in the background, I want you to resume my program by running this function, which is why we call it a callback. Now, while the fetch web API performs its task in the background, without waiting, the runtime will immediately advance to the very next line of code, and it executes it without waiting. The set timeout function also fires up a native web API, much in the same way, and it passes it a callback to execute once that time is up. Our IndexedDB query works pretty much in the same fashion. It fires up a native web API, which receives a callback to execute. So now what? In most programming languages, at this point, your program dies. So if you're running it in the terminal, suddenly the terminal quits, and it shows you your prompt. Or if you were running a GUI application, maybe your GUI dies. Not so in the web browser or a node. Notice that we still have those things on the right. We still have those outstanding web APIs that still have these callbacks. So even though we don't have anything on the call stack, which represents what code we're currently running, there's still some code that would be run in the future if it was given time to complete. We have those web APIs all crunching in the background. So let's say the IndexedDB query finally finishes. This is a natively implemented API. So what it will do is it will alert the JavaScript runtime by pushing that render callback we handed to it onto a queue, which we very imaginatively named the callback queue. Now this doesn't actually yet run the render function. It just kind of queues it up to be executed. The event loop is really just that little, the arrow mechanism there, and all it does is it checks to see if there's anything currently running, or in other words, is there anything already on the call stack, and if there isn't, then it just pushes it over. So if the answer is yes, that the call stack is empty and there is something on the callback queue waiting to be run, the event loop just pops that first callback off the queue and pushes it onto the call stack, which basically just means our render function, our callback, is now executing. But now, while that render function is executing, another web API might finish its background work. Perhaps our AJAX request finally wraps up. So the web API will immediately push the parse function onto the callback queue. However, this time there's already code being executed. So the parse function will actually remain in that callback queue. This behavior is called run to completion. It basically means that the render function is going to finish running before anyone can interrupt it. In this case, the parse function is just going to have to sit down and wait a while. So the nice thing about this is that it guarantees that the currently executing function will finish without being interrupted and wreaking havoc. So when the current function on the call stack takes a long time to finish, it literally blocks that event loop mechanism by preventing any callbacks in the callback queue from being executed. Now during this time, the timer API might also finish up as well, and all it does is it just pushes its callback, in this case the refresh callback, onto the callback queue and waits to be executed. And they just sit there. They just wait. At some point, hopefully, that render function finishes running, and once it does finish, the call stack is now empty again. There's room for code to execute. So we pop off the first callback off the callback queue and move it on over to the call stack, where it's now being executed. And then we wait again until that's finished, and finally, once that parse function finishes, the call stack is again empty, and we can push the final refresh callback onto the call stack and execute that last function to completion. So in summary, while our own JavaScript code is indeed single-threaded, meaning there's one call stack, there's only one function running at a time, in the background, the native web APIs can be executed on separate background threads, which basically means our JavaScript code is orchestrating a bunch of background work. The orchestrating code that you write itself is single-threaded, one thing at a time. But the stuff in the background can in fact be doing multiple things at a time. Now, just for the cognitive model, it helps to think of every one of these native async web APIs as something running on a separate thread, but that's not always the case. The mental model just holds, and it helps explain why Node.js and JavaScript in the browser can perform so much work concurrently while appearing single-threaded. Lots of cool benefits to single-threaded architecture. We don't have to think much about things like variables changing out from under S, or reentrancy, or all these other crazy concepts that are way above my pay grade. Don't have to think about that. Now, I hope that recap just helps kind of set the stage for the rest of the session, but you do owe it to yourself to go watch someone else's much better explanation. Go check this out, bit.ly/event-loop-help. It's a talk by Philip Robert from Scotland JS. It's called Help, I'm Stuck in an Event Loop. And I have to admit, it took me 4 years to finally figure out that pun. Now, the event loop is really great, but in Node.js, you can pretty soon hit a scaling limit with a single process, despite the many background threads. So at this point, many developers tend to turn to Node's cluster module, or they'll turn to an NPM module like PM2. But if you turn multiprocessing too soon, it negates a lot of the single process benefits and the predictability of having that one call stack instead of multiple ones. Now, luckily, a single JavaScript runtime can actually orchestrate an amazing amount of work, as we've just seen. But to write code that will scale easily and doesn't look like a bunch of promise.all spaghetti is quite challenging. So we'll actually need a few patterns, and that's where the more interesting, useful part of this talk comes in, the different patterns you guys can use right now to write highly scalable code that doesn't look like spaghetti. So for the remainder of the session, here are the 3 patterns and recipes we're going to cover. You can use them in Node.js or your front-end apps. Yes, your front-end apps can be multi-threaded. In fact, I was just visiting a video site the other day, wondered why my computer was at 600% CPU usage. Guess what? It was the web page, probably trying to get some bitcoins off me. Or it was Ilya back there.
I'm here.
Oh, over there. See, he's already hacked his C. So our goal is to use this to write highly scalable applications in both the front end and Node.js on the back end without third-party libraries, no frameworks, no fads, just plain old JavaScript. What is this magic? So first, we're going to start off with how we can coordinate concurrency with the pattern. I'll just call it Async IIFES. I don't actually know if there's a proper term for it or not. Maybe it's coined. We shall see. But when you want to do more than one thing at a time, usually you need some really ugly pipelining to describe how those different tasks relate to each other. Let me give you a concrete example. Let's say that we're building iTunes in the browser. And we're beginning to write the code for importing MP3 files into our music library. Now in the browser, you can imagine that the user could import stuff by dragging and dropping their MP3 files onto the application window, so we could import it. Now there's probably 5 steps we could imagine to importing a song. First, we need to read in the MP3's file contents. Then we need to parse out the song's title, its album name, some other useful metadata. Now, in most MP3s, this information is encoded at the beginning of the file. It's a format called ID3. And if you're interested in how to parse this data in JavaScript, there is a blog post on it, bit.ly/mp3-parser. Lots of bit.ly links for you guys. Now, unfortunately, ID3 metadata rarely includes the song's duration for some unknown reason. So we'll need to calculate ourselves with the web audio APIs. Once we've got all that metadata, we're going to auto-create a new album in our local database. Say we're using IndexedDB. And if one doesn't already exist in the database, we'll create one. And then finally, we need to create a new song entry in our music library using all that data we just compiled in the previous 4 steps. So there's a lot of data going around here, a lot of dependent tasks. So here was what my first solution to this look like. Hopefully you guys can read it. Font size is a little small. Let me just walk you through it. First, we read in the file. In this case, I've written some functions I'm hiding for now. One called read, which basically takes in a file you've dropped in and reads it in as an array buffer, binary data. Then we use a parser function, which you could imagine is a separate library, to read out this ID3 metadata from the MP3 file. And then we might split it off into metadata that's relevant for the song and metadata that's relevant for the album to which it belongs. Then we might use the web audio APIs to calculate the duration of that MP3 file, which takes a little while. And then we would finally import the album, go ahead and create it if one didn't already exist. And then as the last step, we kind of wrap up all these loose ends to create a new entry in our music library, a new song. And at the very end, we return the ID representing it. So async and await that you're seeing here, the new ES 2017 syntax for working with promises, is really awesome. Instead of having all those cascading .then callbacks, we can just await the return promise before advancing to the line of code. It looks pretty much like any other programming language where you don't have the event loop. However, there's actually a pretty significant problem if you start importing a lot of these MP3s. We're actually blocking too often. If you start parsing through this code a little bit and squint, you might notice that to import the album, we only needed some album metadata to be parsed out of the MP3 file, which in turn relies on the parser function to complete. We didn't need to know the song's duration, and yet it's blocked until we calculate the song's duration. So unnecessary blocking. These operations could actually be executing concurrently instead of having to execute one by one, because after all, JavaScript knows how to do multiple things at a time thanks to the background web APIs. But if we try to optimize our code so that way it can have concurrency, the only way we can do that is by sacrificing our nice, elegant await syntax. Await is nice because it literally says, let's block JavaScript right here and wait for this promise to resolve. Well, as soon as you put it in await, you lose out on the benefits of JavaScript's default concurrency model. So is there a better way? Well, we could use promise.all to block further code until the file reader and that parser have finished before computing the song's duration and importing an album. The fact that you guys might have a little trouble reading this should hopefully hint that this is not an awesome solution. It uglified the code quite a bit, but more disturbingly, it's actually not even an optimal solution. If you spend a little bit more time trying to come up with an optimal way to break up your code into concurrent chunks, you would find that if the file reader finishes before the parser, that the import album function could actually begin executing immediately. In other words, despite us trying to optimize for concurrency here by allowing tasks to run in parallel, we picked suboptimal groups of tasks to run in parallel. Now this is one of the more readable ways we could try to optimize our code, but it turns out we have to come up with that optimal solution ourselves. And it takes a fair amount of work to figure out the optimal grouping of parallel tasks, and switching any of these steps from a synchronous API and swapping it out for one that's asynchronous actually completely changes the solution. So that means a lot of code churn, a lot of really irritated colleagues who are looking at your big Git diffs and wondering, well, I only changed one line. Why has this entire block of code suddenly changed, and why are there 15 more promise.alls? Not great. Thankfully, there's another way we can model these concurrency relationships. And the key observation is this. What if we modeled every chunk of code as a dependency graph for the runtime to evaluate, like we did with my to-do list for giving my talk in Budapest? In other words, what if we took every single thing and considered it to be its own little chunk, and then we just kind of strung these together and said how they depended on each other, and then let JavaScript automatically execute them in the optimal order? This should sound a lot like how makefiles or gulp files or pretty much any task runner works. But we don't need libraries to do this. We can actually just use built-in patterns in JavaScript. So to accomplish this, we're going to use a pattern. It's called async immediately invoked function expressions. Quite a mouthful. Most of you are probably already familiar with IIFES, immediately invoked function expressions, a function that you create just to immediately invoke, basically just so you have the benefits of scope, so that way you don't leak variables into the global scope. Well, now imagine creating an async IIFE. This is an IIFE that returns not the return value, but a promise representing that return value. A lot of you are already playing with async functions. I say already, they have been out for a while, I suppose. But a lot of you are already using it in your day-to-day code. You might recall that all async functions return a promise. That promise, when unwrapped, when it resolves to the return value of that async, or excuse me, of that function. Now what we're doing is we're creating an async function and then immediately invoking it. What on earth are we doing? Why would you create an async function like this and immediately invoke it instead of sticking it somewhere else so you could reuse this function over and over again? So the async IIFE allows us to group together sequential code into a single unit called a task. And then it immediately invokes that task, much like Go. Now a task is pretty cool because it can actually depend on other tasks as a source of input, and it produces one output as the return value as its result. Now since this is an async function, the task local variable that you see on the left will be a promise, which means we can use that maybe in other parts of our code. Now, if there's one thing you take away from this talk, I hope it's this design pattern. It, again, should feel a whole lot like working with gulp or a makefile, pretty much any task runner. Key observation in here is that we immediately start running the task, but the very first line in that task, we wait, potentially for other things to finish, other promises. So if we had another task that was up above this one, which would be a promise, when it resolves, it'll be whatever the return value of that promise was, and we're feeding it into this task, but then we're awaiting it, which means we're blocking and waiting until that other task completes. And then at the end, we finally do some work, and then we return, or rather, this particular task resolves to some useful result that we can use elsewhere in our code. So if we were to take this pattern and apply it to the code I just showed you guys, here's what it would look like. Now I've zoomed it in a little bit here so it looks a little bit longer. It's not much longer actually, and moreover, it's actually far more resilient to changes over time, which is pretty cool. So if we refactor our MP3 importer into these multiple tasks, here's one way we might break it down. We would have the read task. You'll notice that there's actually not an async IIFE here. I've just assigned a promise, which is what this read function returns. I've just assigned that promise into a local variable. Totally fine. I didn't need to stick that in an async IIFE. The next one, which reads out the ID3 metadata, the first thing it does in there is it awaits the result of a parser, which might be a third-party MP3 parsing library. It awaits that before it extracts all this metadata, and then the return value, or what this task results in, is going to be some useful metadata, song metadata, album data, etc. Then we have the album import task, and all it needs to know is when has that meta task finished? When has the code that tries to extract all this metadata finished executing? That's all I'm waiting on. Once it gets that data, then it creates the entry in the database, and the result of this task is an album ID. That is finally fed into the last task, not this one, duration task, very similar to the others. In this case, it only waits for the file to be read in before it can do its thing. But the last step, and this is kind of the step that ties everything together, the song import task, it needs to have the album ID, all the metadata, and the song's duration before it can actually create this entry for this particular song in our music library. The end result of that entire async IIFE is just a song ID that we can use later on. And then we have the very second to last line of code here, which kicks off the entire process. Await song import task. If you remember your await and async syntax, song import task is a promise. Awaiting it blocks that particular function until that promise that's in song import task has resolved. Whatever it resolves to gets put in the local variable song ID, and that's what this entire importer code resolves with. Now the cool thing about this is that with multiple tasks, we're actually just leveraging local variables and concurrency by default to essentially create a dependency graph. One which the JavaScript runtime knows how to optimally evaluate for us, no matter how complex, no matter how much you change up this diagram. The cool thing is we didn't have to explicitly define any execution order. Much like with gulp or other task runners, you don't tell gulp, here's the order you need to execute things in. Instead, it just kind of pulls on one of those tasks and there's all these strings attached to it. And as it pulls, it starts executing that code. So the JavaScript runtime will optimally evaluate this graph for us. We didn't have to explicitly define anything. We just wrapped sequential chunks, these logical chunks where every single line depends on the previous line. We wrapped all of those in async IIFEs, and we modeled the constraints and then let JavaScript figure out how to satisfy them. That's pretty cool. No libraries. So there's so much more you could get out of this particular pattern. So again, I'm going to forward you guys to another blog post. Async-IIFE, that's 2 I's. Check it out. Much longer blog post. Pretty much the same code. So if you're interested in seeing it up a little bit closer, go check it out. But our second step is how can we create scalable code to define execution preferences? Up until now, we've looked at how do we state these execution constraints. In other words, this must happen before this. Those are constraints. The other part is preferences. In other words, how do we tell JavaScript, I would rather these things execute first before this one does? Those are our preferences. They don't have to be satisfied, but it's something we would prefer. So in particular, One common preference is throttling, and that is how many of this particular task should run in parallel. And we can specify this with some functional programming methods. So right now our MP3 importer runs as fast as possible, does as much concurrency as possible, which is fabulous. But you are running this code in the browser, and so we need to be considerate of the user's CPU, which is, after all, a very limited resource, especially if you're on a little 12-inch MacBook like I am. So Async IIFES let us define those execution constraints, but how can we declaratively describe our preferences for how work gets executed on the CPU? In our app, for example, iTunes in the browser, what if a user drops a huge collection of MP3s into the browser? We might not want to start importing all of these all at once. Not only would that be a horrible experience for the user because they're like, wait a minute, why am I having to sit here and the progress bar isn't moving? Well, it's because it started importing everything at once. But moreover, you're probably going to lock up the browser because the browser's like, gosh, I've got too much work going on and now this person's trying to open up YouTube because they're bored. I just might as well go die or pretend that I'm out of juice. Make your laptop happy, make your users happier. We don't want to have this kind of behavior. We wait, and then suddenly it jumps. That's just because all those songs import at the same time, which means the progress bar becomes meaningless. The browser just locks up, makes users frustrated, you lose your users. What we would rather do is just import a few songs at a time, and then queue up the others for import whenever another song finishes importing. Or if we were to imagine a little queue over here that has room for any number of people, but then we have 3 stations that can handle those people, we can handle 3 people at a time, but meanwhile we queue up everyone else. That means we actually get people through the line and don't completely overwhelm the cashiers. That's basically what we want to do with this code. There's a lot of different ways you can do it. The main way you'll see in threaded languages is you would do this with semaphores. Semaphores are pretty much just a special way to represent limited resources. So with a semaphore, you can limit concurrent access to a shared resource, like the CPU, a database, network I/O. And at their extreme, we could limit access to just one client at a time. We could call this a mutex, a mutually exclusive lock. Now, in an object-oriented paradigm, what we might do is we might have a special kind of object called a semaphore. We initialize it with the maximum number of concurrent clients that are allowed to acquire this semaphore at the same time. And then we would use await to acquire or wait for a spot in the queue. Once a spot opens up, we do some things, and then we release our spot when we're done, so that way another client can start executing some code. So here's a sample object-oriented solution to creating a semaphore, pretty standard. It just tracks functions that are waiting to be executed, and whenever a spot opens up, it executes the next function in the queue. It's not much code, it's pretty short. It's not the best solution though. There's actually some really brittle boilerplate here with the traditional semaphore model. We could very easily write code that will acquire a semaphore, or in other words, get a spot at the cashier's desk, but never release it. So this is like someone really irritating who just kind of comes up to the cashier and just starts having a conversation, and they never leave. Or worse yet, they have a heart attack and they drop on the floor. They call the police, and then the cashier just sits there wondering, is this person going to come back? Are they going to come finish up their order? Are they going to finish paying for this? It's a rough situation to be in as a cashier. We don't want that. But in fact, that's exactly what can happen here. Let's say we throw an exception. Well, guess what? Now it blows up all the rest of the function, which means we never release that semaphore. The way to get around this is you'd have to wrap that entire chunk of code in a try-catch statement. And you have to remember to do that every single time. Not cool. So instead, here's a functional programming version of a semaphore. Instead of returning an object, it's actually going to return a higher order function, a function that wraps around another function. Those of you who do a lot of React hear a whole lot about higher order components all the time. Well, higher order functions, same deal. It returns a higher order function that wraps around other functions with a call to acquire and release. So here's roughly what that looks like. At the bottom, you can see kind of the code I was talking about, where we acquire the semaphore, then we run the code that could potentially blow up. We catch any errors and make sure at the very end to always release the spot, so that if some way someone does drop dead at the cashier's desk, at least someone else can check out. To use this functional semaphore, we invoke it and pass it in async function, which represents a limited resource, a limited time slot. Now, there's no way that a semaphore can be acquired but not released because we've wrapped all this code in a big try-catch to make sure that no matter what happens, even if this code blows up, we always give back our slot in the queue. We always let someone else come up to use the cashier's prowess. So now we're pretty close to an elegant higher order function, actually, where we can simplify this even more. Let's say that we have this function called import mp3. It's already an async task. This would basically be all that code we just wrote. So let's say that we want to limit how many times that import mp3 function can be called and be running concurrently. In our example, we said, let's just let 3 songs be importing at the same time, and then whenever one of those songs finishes, queue up another one. What we could do is we could create a function. We'll call it a decorator or a higher order function yet again, and we'll call it limit. And what it's going to do is it's going to take in any async function that usually runs with unlimited concurrency and returns the same function, but now composed with throttling behavior. That's a beautiful word in functional programming to talk about composition or nesting these different behaviors and stuff. It's one of the reasons higher order components are so cool in React. They're equally cool just in your day-to-day work. So this example would take our mp3 importer function, which is an async function, meaning it takes a while for it to complete, and it returns a new function that looks exactly the same, but no matter how many times you invoke this limited import mp3, it will only actually run the underlying import mp3 function at most 2 times concurrently. And now as soon as one slot opens up, it'll start running the next instance, but meanwhile, if you keep calling limited import mp3, it just keeps queuing up these things in the background. So song 1 and song 2 in this example would immediately begin importing, but song 3 won't even start importing until song 1 or song 2 finishes. The really wild thing about this is that the way we make use of our import mp3 function has not changed. We have no difference in APIs. We can actually use this limited import mp3 function anywhere we would have used the regular mp3 importer code. One of the hallmarks, hopefully, of functional programming is being able to swap in different things that have different or better behaviors, but have exactly the same API. So the limit function is really easy to write. It's actually just a few lines of code in ES 2015 style. We can write it really easily with that semaphore we built. Basically, we just feed in what's the max concurrency for this function. Here's the function. We create a semaphore, and then we return a higher order function, which just wraps around the original function we gave it. So when we give it import mp3, it gives us a new import mp3 function that looks exactly the same, except no matter how many times you call it, only 2 instances of import mp3 will be running at a time. Again, this preserves our existing API throughout all the rest of our code base, so throttling concurrency does not require you to refactor your code or change how you pass things around. Again, I'm going to send you into another blog post. A whole lot more we could dive into here, so feel free to check out the source code for that particular implementation on GitHub. It's called semaphore.js. Really short, really simple, may not even be worth importing into your NPM module because you're like, what? This is like 30 lines of code. I should just put this in a file. Now we get to the final component of this talk. I see my students back there and like, help, we got to get up early tomorrow. We're getting there. The final component of this talk, we're creating our own long-lived async tasks with a web worker cluster. What is all this jargon? Well, the browser comes with a huge selection of async APIs, and they're all natively implemented. Fetch, IndexedDB, set timeout, Bluetooth, tons of really cool APIs. Funny thing is, every time I look at this slide, I think of Apple's developer conferences, and they show all those cool new APIs that have been introduced, and most of them just relate to something obscure like new locales, something incredibly useful. Now, under the hood, the browser actually manages a dedicated thread pool that's ready to crunch those async APIs for you. So they're all standing by, waiting to handle your work. But how would you make your own native async API for long-lived async operations? Let's imagine that you're implementing PGP from scratch. Well, PGP and a lot of execution or encryption things take a while to do, because one of the fundamental parts of security is it needs to be hard. It needs to take time. So what if we wanted to move these off the main browser thread, which if we did that, If we didn't do that, the browser might freeze up, the user might be scrolling, and suddenly it freezes up as you send your PGP message. We wouldn't want that. So what if we could move it to the background by basically creating our own async API? The problem is we're not experts probably in C++ or whatever the Chrome runtime is written in. So we don't want to go write C++ APIs. And moreover, we can't share that with anyone. Not everyone's going to download our patch, i.e. hacked, version of Chrome just so they can use our PGP library. So what if we want, in our case, to move all this MP3 importing code off the main thread? So that way we can keep it from locking up the interface. Well, web workers are essentially that. They're a standard web API for creating background threads. Now to create a web worker, all we have to do is we invoke the worker constructor and give it the path to the JavaScript code that will execute with its own dedicated scope and its very own event loop, completely isolated from the main thread, which is what we normally work in. Now to communicate with the worker, the only thing you can do is exchange messages. The worker has to be listening for an incoming message and then handle it as part of its own event loop cycle. So very much like how you have to add an event listener to listen for a click, and that will be handled as part of your event listener cycle, your event loop cycle. With workers, they can receive messages, and that's handled as part of their event loop cycle. Now the cool thing is the main thread and the worker thread don't need to block to sync up and exchange messages. They actually just send and check for message when they're ready to. They have a mailbox that's sitting there waiting for anyone to throw a message in, and just when the other thread is ready to check in for new messages, it goes to the mailbox and pulls the latest message out. Now unfortunately, the basic web worker API is really not that elegant. When you want to have a two-way conversation between the worker and the main thread, which becomes necessary when we want to build these more complex multi-core applications, it really quickly turns into callback soup. So what if web workers looked more like an async web API call, where we invoke it and we get a promise as a result, and it resolves to the worker's end result? In other words, something that looks a whole lot like the fetch API or these other natively implemented async APIs. That would make it much more trivial to move CPU-intensive computations to a separate thread, so that way we don't block the main thread, while at the same time ensuring that we don't even have to think about things like reentrancy or dealing with multi-threading or deadlocks or any of those crazy things. Well, here's what we could do. We could move our MP3 importer code into a worker and treat it like a native async web API with just a little bit of glue code. We're going to create our own function. I've just called it cluster. I realized after the fact that's a really bad name. Probably just call it async web API. And we're going to use this special function to kind of take a web worker, which we can only talk to with messages, and wrap it in such a way that we can treat it like a function that returns a promise that resolves to the end result of that worker. Let's make it a little bit more elegant for our use case. With functional programming, the implementation for cluster is pretty terse, albeit there's quite a bit going on. Again, this is up online if you want to do a little bit of a deeper dive. What it does is it creates a bunch of web workers. It creates a pool of them. Usually it depends on your how many cores you have on yours. If you have a dual core machine, the ideal number is 4. If you have a quad core, the ideal number is 8. You can configure this. And in the end, what it does is each time you invoke this cluster, it grabs any unused worker from the pool, and it forwards along some data to get it started on this computation. In our case, this could be it forwarding a file to import as an MP3. So each time it's invoked, it grabs a worker from the pool, forwards along some data. Once the worker finishes and replies with the result, it's added back to the pool, so that way someone else can make use of that worker. And the overall promise for that async web API we just implemented evaluates to that final result. Now the code for the web worker itself, which is what's going to be doing all the actual work, is really short. It's actually an infinite loop that just receives data from the main thread, in this case, certain MP3 files to import, and every time it gets one, it does some work, and then it notifies the main thread when it's done with the computation. By the way, this isn't just for the browser. You can actually use a library to write web workers in Node too. Pretty sure there's a native multi-threading implementation of Node, but if you want to preserve your interface between your front end and your back end applications, you can actually use a web worker library that under the hood uses multi-threading, native multi-threading at that, but it looks exactly the same as creating a worker, so you can build code bases that are highly scalable and yet look exactly the same from the front end to the back end. So to wrap this up, TLDR. JavaScript in the browser and Node is really highly concurrent out of the box. The challenge is actually how do you keep it from doing certain things in a predetermined order. So async IIFES are one way. They help us define execution constraints to take advantage of the machine's multi-core capabilities. And thanks to the event loop, we don't need to worry about thread safety at all, or reentrancy, or any other host of problems you would normally have to think about pretty deeply in, say, something like C++ or Java. Functional programming patterns keep us from making a mess of things when we want to encode our preferences just for the sake of multi-threading. They allow us to basically drop in some throttling behavior, a lot of other different behaviors. Anytime you hear the word behavior, think functional programming, think higher order functions. And finally, when you do have something that is computationally intensive, you can create your own async web API for it just by creating your own web worker. To make it nicer, there's some little libraries. You can go copy paste some of my code to basically wrap up a worker in a promise-like interface. So the next time you're trolled, just remember you can always bet on JavaScript to help you leverage those multi-core machines, mine more Bitcoins, and crunch your to-do list so that way you, unlike me, you won't soak your favorite book in the shower getting ready for a conference. My time share on this room CPU is up, so if you like pretty pictures and travel stories, shameless plug, you can go hop to my landscape photography site, yellowscale.com, or find me on Twitter as @Nibbler. I'm an Atlanta native here, so you can also find me that way, because we're 10 minutes up the street, 3 minutes by run. What questions can I answer? Yes?
All right, two parts. So with a worker, do you actually have, or do you get to allocate, what function goes to what, core, or it figures out all that out automatically?
With my naive implementation, it doesn't. It assumes that all those workers do the exact same thing. Better implementation would do something where, say you have an MP3 importer and you have some code that does crypto. Those are two very different worker pools. And so what you might do is create a worker that's a little bit more generic and knows how to do any of these computationally intensive things. Or you might just not go that extra mile and you might just spin up one worker at a time for the particular computationally intensive thing you need to do right when you need it.
So each worker is one core, like one worker, one.
Or rather, each one of those is, so cores are typically split up into 2 threads.
Okay.
I don't quite understand it myself, but if you have one core, it's best to have 2 threads.
Mm-hmm.
And so if you have a dual core machine, you would have 4 workers in the pool. And basically, they're all just standing by waiting to do work.
Got it. Do you have a GitHub project for everything that, this MP3 player that you built?
I do. That said, probably be easier to go back to the bit.ly links. So I'll make sure to flip back to those. I think it was bit.ly/mp3-parser,
Okay.
bit.ly/event loop help, bit.ly/semaphore.js.
Yeah, I got those.
Excellent. Yes, those would probably be the best place to go. And then I'm also November Yankee Bravo Bravo Lima Romeo on GitHub, if you can remember that. Yes?
So we've written applications a couple of times where we need to get notifications from the server side to the client side, and we've had different implementations. One being where we do more of a push style using WebSockets, and one where we do more of a pull style using web workers making HTTP calls to the backend. Do you have any advice on the benefits, pros, cons of either of those approaches?
Probably not so much. I would definitely lean towards WebSockets because they are very lightweight, very fast, but if you expect to do a lot of computationally intensive work as a result, then you might want to offload that part to a web worker, but maybe let your main thread deal with all the WebSocket stuff.
Sure.
Yes?
So there's, I caught bit.ly links for like the Semaphore.js and such, but I didn't see one for doing the web worker jumpstart to do the web worker cluster.
Yes, I think that one's also under Semaphore.js.
Okay.
Should be. If it's not, and I'm a liar, come find me. Yes?
When implementing your own workers, if you don't set the constraints to how many are able to run at once, how likely are you to run into an issue where your own setup or a user that has lower specifications than you expect is to be overrun with those and stack up too much.
You definitely could run into that situation. Generally, your CPU is already very good at dealing with a lot of things being thrown at it. It's just, it turns out the optimal number is usually twice the number of workers, but you're absolutely right. What happens if you've got iTunes in the browser open one tab, and then in the other tab, you've got this other intensive applications? Well, now you're kind of probably overtaxing past the, the optimal number. But that said, you could very easily spin up 100 workers and not have much extra overhead. So really, it's a little bit of a micro-optimization. But some tuning can help, and Chrome in particular is really good about throttling background tabs, so that way the one that is currently showing can take the most advantage of CPUs. Which means for this guy back here, if he wants to create some Bitcoin mining stuff to run on my machine, and it's in a background tab, you're out of luck. Other questions? Excellent. Well, thank you so much for your attention.
All right, hold on.